Okay, so let's start with the first topic. So robust classifiers. In particular, I'm interested in evolutionary strategies and so-called topological data analysis. And these two ideas can be embedded in neural networks in some way to increase their robustness. Right. So we want to design algorithms for image classifiers that are robust with respect to perturbations. So the perturbations of pixels in particular. So you see an example how dramatic this can be. You know, when you run FSGG fast gradient sign method, for example, to produce adversarial examples, it fools the neural network completely, right? So instead of cat, you add some invisible noise, and the neural network thinks that it's like a shrimp or whatever, yeah. And this is really bad property because for mission critical deployments, you want to have you want to be certain that something like that won't happen, you know. So your deployed solution will be safe. Okay, there won't be possible attacks in particular. So so that's why there's a lot of interest in designing robust classifiers, and there are many ways of achieving this. So this is the slide that I showed you already. So how fast gradient sign works. So we have image. You compute, I mean, some adversary computes so-called nematode. So it's like a direction which use the gradient to find the direction which will be the most devastating for the classifier, and you add it to the input image, and suddenly, with high confidence, classifier thinks that it's something else. And there are many examples. Again, this in particular is crazy because this example on the left is already adversarial. So it's not the neural network is fooled to think that this cat is in fact guacamole. But someone rotated this cat, and the neural network is again working properly. Okay, so it outputs the correct class after this rotation. Okay, so this effect is really unstable of adversarial examples. So it's really some weird property that we want to get rid of. Yeah. Even if you have like okay, there are many examples like that. So there's like adversarial patch. So there's some classifier working online, and someone puts some weird patch, and suddenly it breaks down the whole classifier, and instead of banana, it thinks that there's like a toaster. So why this is possible? So these most devastating attacks, they're white box attacks. So they're based on propagating the gradient. They're based on actually, so the white box means that adversary, it has access to the architecture. So in particular, adversary can compute the gradient, okay, with respect to input, okay. So what happens when you compute the gradient with respect to input? You can see how devastating it can be if you for example just take the fast gradient sign. So you just take a sign and you pick like the kind of the corner in this high dimensional cube, and you pick it according to the gradient sign, and then you obtain the most devastating direction, and you just add some small perturbation in that direction, and it completely destroys. Okay, so again, this is possible because especially for deep networks, when you have access to get to the architecture, you can compute the gradient with respect to input. Okay, the gradient with respect to input of the network tells you how to change the input image such that the output is drastically different. Yeah. So all of the most powerful attacks are based on this principle that you have some gradient, involved in there, and it assumes, okay, white box. It means that it assumes that you can actually compute it because you have access to the architecture. Okay, the things get complicated. The things get complicated when you don't have access to the architecture or you cannot compute the gradient. Okay, and these are the paths. These are the paths that I find interesting. Okay, in avoiding in this direction that we want to make our neural network classifier immune to the adversarial attack, right? So let's start with the most common ways. Okay, so how people, okay, as I said, this is like really bad property that everyone wants to get rid of, and actually no one knows how to really do that. And there are many approaches. The most common ones are possibly related to so-called adversarial training. So the idea is that why not to generate, okay, so because we have freedom of choosing the training set, okay, so why not to add adversarial examples into the training set, okay? That sounds great idea, yeah, okay, we will add the adversarial examples to the training set, and then the neural network will learn to recognize them as a correct class. And this, as you can imagine, this doesn't work because this is there are many possible directions that you can perturb your images, and there are many possible attacks that will provide you slightly different images. So it's impossible to actually train to kind of produce a data set which contains all possible adversarial examples. Okay, because again, this is they can be computed in many ways, and you can construct them using different algorithms, and also you can manipulate with perturbation size, etc. So it's really complicated issue. So you can take one algorithm and produce some examples and add them to the training set. That's fine, but then someone can still, if adversary has access to the architecture, he or she can still produce new adversarial examples that were not present, okay, before. So adversarial training is not sufficient to get rid of that issue. And it's kind of, adversarial training is like trying to patch something which doesn't work. Okay, so the core of the issue, lies in the fact that there's backpropagation, and that you train your neural network using that algorithm, and also there's a possibility of using backpropagation to maliciously modify inputs. Okay, and so you know, so using adversarial training is trying to kind of patch this construction. But there's, if you know, it's like there are like many leaks in that construction, so you can patch like some of the leaks, but there will be like a new one appearing, and always, right? So it's not sufficient to do this. Another possibility which people use a lot is to do model ensemble and majority vote. Okay, so imagine that, okay, you can say, yes, okay, someone can fool my classifier like one single neural network. So let's build like an ensemble of dozens or hundreds of different neural networks, different architecture possibly, and then it will be harder to fool. And then it will even work better, because to classify images, you can do majority vote. Okay, so there are like all of these classifiers that you constructed, and they, at the end, you have some image that you want to classify, and you run all of these classifiers, and you see the results, and you do a voting. Okay, so the class which received the most votes will be the correct one. And this, at the same time, this should be harder to fool, right? Because to generate adversarial examples for this type of ensemble, because you would need to construct example which works for all of these classifiers which are in the ensemble. But apparently it can be done also, right? Especially dangerous property is that adversarial examples can transfer from one architecture to other architectures. So one example which is constructed for some particular architecture, it will work for also other architectures often. So that's also not sufficient to get rid of this problem. Model ensembles are not enough also. And also, so these architectures are still prone for white box attacks. So another perspective would be to combine deep learning with some symbolic AI. Okay, so symbolic AI, by symbolic AI, I mean something which can be explained. Okay, so as you've seen, neural networks are really hard to interpret. Okay, so you train something which works, but you don't know how. So maybe we should combine it with some symbolic algorithm, which actually provides some interpretation, and then you can see that maybe someone is trying to fool you, because the interpretation will be not will seem not correct. Okay, maybe you will see like let's look at this picture. Maybe we want to construct like topological space, yeah, where we have separation of different classes, and if someone will try to fool you using some small perturbations, you will see that you will still stay in the region where you expect some particular class, but your classifier will tell you that it's something else, and you will detect. By doing this, you will detect. You'll be able to detect adversarial attack, possibly, right? Of course, it's not obvious how to embed this symbolic AI idea, and first of all, what type of algorithm will be capable of providing interpretation in form of a graph, for example, like here. Yeah. So what I been working on is trying to use TDA, topological data analysis, and in particular mapper mapper algorithm. So okay, let's see. So the first idea. Okay, so the mapper algorithm, I will explain you in a second on example, but in general, it will output for a given data set. It will provide you this graph representation of your data set. Yeah, that's what mapper algorithm is doing. So let's see. Let's do the first thing. Let's replace convolutional features. Okay, so in neural network you have all of these layers, and the idea, okay, they can be convolutional or not. It doesn't matter. I told you that actually convolutional networks are not magical in the sense that they can be they can be kind of simulated using MLP, fully connected layers. So imagine that each layer is kind of computing some features. Yeah, that's how deep learning works. So you stack many layers because you hope that you will your network will learn correct representations, and each layer will saturate kind of one of the features. Yeah. So the first idea, let's try to replace this convolutional kind of features, deep learning features, by something completely different. Yeah, let's use the graph representation, the mapper graph representation. Yes. So what is mapper graph representation? So this is supervised learning algorithm using the machine learning terminology. So imagine that you have, so to explain it on a particular example, imagine that you have a point cloud like this, this hand. The point cloud is taken from a hand. And now you prescribe some filter. In this case, it's just projection. Okay, we have three-dimensional point cloud. In general, this is high-dimensional space, like even thousands of dimensions. This can be still done. So let's prescribe a filter. In this case, it's just projection onto one of the coordinates, x. Yeah. So the filter. Okay, you can put a heat map. So you get a red on the fingers, and the more you move to the right, you get more blue colors. Then let's split our image. In this case, some interval of x values. Let's split it into overlapping bins, and let's look at the pre-image of each interval. Okay, so I take the interval of this x values, of small x values, and I will get the tip of the fingers. Yeah. Then I increase x a bit, and I will get another part of the fingers, etc. And okay, so each interval, I have like 6 intervals here, and the pre-image of each interval is some subset of the original point cloud. And then I can cluster. Okay, I can look at each pre-image cluster. I can use like dbScan. Well, what is actually most often used is there's like algorithm called dbScan. You just it's like unsupervised kind of, and it kind of clusters. It's able to compute clusters of data. So this is easy. So I cluster, and then I get a graph. So each cluster becomes a node, and I have an edge in the graph if the two clusters overlap, right? So this is graph representation of my original point cloud. And this is, in a sense, this is like 100% symbolic, because I can see how my data set looks like. Yeah, in low dimensional, this is like one-dimensional structure graph, only edges and nodes and edges, and I can see how my data set looks like, kind of in low dimension. So okay, let's see how could we use it in for image classifier. Okay, so the first naive idea is to replace the dense layers of the neural network with that algorithm. Okay, so the features, so for each data point I get okay, so for the whole data set actually, okay, first I project it onto latent space, and then I construct the graphs, and I get binary features out of that. So these are like different because in neural network you will get some numbers, yeah, but in each layer you will have some numbers for each data point, and here you get a graph representation, so it's binary. Okay, you put a 1 if the given point is in the given cluster, yeah. And then let's classify as usual. Let's classify that using dense neural network, yeah. So it's kind of, yeah, classifier like that. This works for simple data sets like MNIST or fashion MNIST, which is like MNIST with piece of clothing, shoes, shirts, pants, whatever. And this is more robust. Okay, so first of all, you cannot run white box attack on that, in the sense of the gradient attack, gradient-based attack, like fast gradient sign method, right? Because you cannot differentiate, you cannot backpropagate through that. Okay, this looks strange. Why would we do that? But the motivation is that maybe you don't want to backpropagate, and this is perfect because it's hard. It's like discrete algorithm, so it's not differentiable. So the problem with propagating gradient and computing gradient respect to input is gone. So the only thing what you can do is to perturb images using some standard method like blur, salt and pepper noise, or like some random Gaussian noise. You can still try that, and this also kind of, if it's sufficient, it will fool a neural network, and this it seems that it fools less this type of classifier that I present you on this two simple data set. And the drawback is that, okay, how to do it for more complicated data sets. So let's try to combine it with, maybe we should actually combine it with neural network. Because if we have complicated data set, it's like sparse. Like one of the example you can look is called ImageNet. It's like thousands of classes, and each class has only like 500 examples or something like that. So it's kind of even less in MNIST, and the data set and the images are much more complicated because these are like real photos. So it's maybe not a good idea to get rid of like neural network completely, but we can still combine these two things. Okay, so the deep learning, this is actually coming from thesis of my student Piotr Rutkowski. So we trained this kind of deep learning plus symbolic graph-based classifier on ImageNet data, ImageNet 10 dataset, which is like 10 classes from 10 classes of pictures, photos taken from ImageNet. So the pipeline is we have usual deep, many layers, which are convolutional layers. In this, okay, it's not important in particular what is the dimension, etc. Anyway, once we compute the features, we can map them into this topological space and do the classification using SVM, support vector machine, that you know how. It's very simple, and you learned how it works. Yeah? And this type of there are two main takeaways from this type of research. So we make gradient-based attacks impossible. So this is achieved by including, again, non-differentiable component. In this case, I showed you it was topological algorithm, yeah, which constructs graphs, and it's this discrete is not differentiable, yeah. And so the white box attacks, the standard white box attacks doesn't work already, which is already good, because these are the worst, the most devastating attacks. But there are still black box attacks. Yeah, there's this. You can blur. You can add some random noise. You can add salt and pepper noise. But still, for this type of attacks, this type of the architectures, like this example of architecture of image classifier works better than pure neural network. So yes, so right, I showed you that we can use kind of topological algorithm as this symbolic way of enhancing neural networks. Is there like another way? So let's look at the perspective beyond backpropagation. So what if we don't want to use, okay, because there are a lot of issues are coming from the backpropagation itself, right? Because it has this property that if there are a lot of layers, you will kind of stack a lot of computations, a lot of products that will accumulate, you know, and you will get large gradients out of small changes in inputs. Is there another possibility which goes beyond backpropagation? So, and also, I recommend you to read this paper. So, of course, there's no any evidence that that backpropagation is used by the brain, okay, the human brain, for learning. Obviously, it's not what you expect, yeah. So maybe we should use something else. So one strategy, which is definitely interesting, is to employ evolutionary algorithm for training. So, right, evolutionary strategy in itself, it can be easily simulated. You just generate some random networks, you see how they perform, and you pick the best ones, and you mutate them, and you receive the next generation of networks, yeah? And you can repeat it, and by doing this, you will train something, okay? You can also what people are doing a lot is even to choose architectures, to find optimal architectures using evolutionary search. So that's definitely maybe something to try. Okay, if we do this, if we will avoid the issues with adversarial attacks. So that's another possible perspective.